What is quantum computing? Quantum computing focuses on the principles of quantum theory, which deals with modern physics that explains the behavior of matter and energy at the atomic and subatomic level. Quantum computing makes use of quantum phenomena such as quantum bits, superposition, and entanglement to perform data operations. Unlike classical computing, where the term bit represents information conveyed by computers, quantum computing uses quantum bits or qubits for a unit of memory. For example, on a classical computer, transistor can be on or off, which indicates the 1 or 0 used to compute the next step in a program or algorithm, a reason classical computers are also called binary computers. Qubits, on the other hand, can actually be both at the same time. This can be explained by a phenomenon called superposition. These two concepts must be thoroughly understood before we look deeper into what quantum computers can do and how. In classical mechanics, as we know, the term superposition is used when waves overlap. They interact so that they may cancel each other out, combine to increase in magnitude, or do a combination of both. In terms of quantum mechanics, however, superposition is a little different. Here the term describes a particle existing in multiple states at the same time, instead of being in a single state, or being in the process of changing between states. This happens because particles have wave-like properties at our quantum scale. Just like how waves overlap as we mentioned earlier, we can think of this phenomenon as states of quantum particles overlapping simultaneously. The go-to example of superposition is a flip of a coin, which consistently lands as heads or tails, a very binary concept. However, when that coin is in mid-air, it is both heads and tails until it lands, both heads and tails at the same time. This is just like having to assume that Schrödinger's cat is both alive and dead at the same time before it is measured. Quantum entanglement, then, describes quantum particles whose properties are connected to each other, even when they may be spatially separated. These properties may include momentum, position, polarization, etc. Therefore, measurements performed in one system instantaneously influences the entangled systems. This can be applied in quicker transmission of information, for instance. Let's look at an example to help us understand this rather mind-boggling concept. It is possible to prepare two particles that when one particle is in the up state, an entangled particle would always be in the down state, and vice versa. Let us assign them the numbers 0 and 1 respectively. Now suppose we have two qubits where we can have different combinations of these two states. In other words, we may either have 0, 1 or 1, 0 in each of the qubits. If we want to normalize the two qubits as if we only had one qubit, we have to put them in superposition. We mentioned earlier that superposition is when particles may have multiple states at the same time. In such a way, in our system now, each qubit is either 0 or 1 by a 50-50 chance. The states of the two qubits are random, but it is critical to keep in mind that they are dependent on each other. Therefore, combinations 1-0 or 0-1 are possible, but the qubits together cannot take the forms of either 1-1 or 0-0. When we try to measure the entangled system, the system would collapse into either of the two possible states. Using the principles of superposition and quantum computing, quantum computers can process calculations simultaneously. This allows complex calculations like factoring with very large numbers which classical computers cannot do. They can also transmit information almost instantaneously, allowing advancements in areas including communication and cryptography. An example of a practical application of quantum computing using these principles is quantum key distribution, or QKD. One-time pad is a common and safe cryptographic protocol used widely, where a secret message is transmitted between two parties. The main difficulty with this traditional method had always to do with the distribution of the key. QKD, however, may now allow the distribution of these keys at a distance. The security of QKD relies on quantum mechanics property that any attempt to observe or measure a system will disturb it. Alice, a device at the Institute of Quantum Computing headquarters, would receive half of the entangled photon pair generated at the University of Waterloo, for example. Bob, at the nearby Perimeter Institute, would receive the other half of the entangled photons. The polarization of each photon is random, so it is impossible to know the unique properties of a photon in advance. Depending on the polarization, Alice and Bob will ascribe either 1 or 0 to each photon received, and the string the two receive should be the same. Should an eavesdropper attempt to spy on the signal, this would disturb the system and Alice and Bob would instantly notice that their strings do not match. IBM Q is the world's first ever circuit-based commercial quantum computer introduced by an American computer hardware company, IBM. The 20-qubit computer was only recently developed, revealed to the rest of the world in January 2019. Let us first explain the structure of the IBM Q quantum computer. As we have already explained, quantum computers manipulate information using qubits instead of bits. To create optimal conditions for qubits, the computer must be kept very cooled, as any heat in the system can introduce error. So the computers are designed to operate at temperatures near absolute zero. A quantum computer's dilution refrigerator is thus designed extremely sophisticatedly with more than 2,000 components, exploiting the mixing properties of two helium isotopes. Due to the extremely delicate structure of a quantum computer, the computer cannot be available to everyone, obviously. However, we can access the Quantum Cloud service to build and run our own quantum circuit on the IBM-Q homepage. Quantum circuit is a model for quantum computation. A computation is a sequence of quantum gates. This picture shows the circuit composer, which includes gates, barriers, and operations. This picture explains what each gate does in the circuit, but for the purpose of this video, we will not explain them in further detail. One of the most appealing characteristics of IBM Q is that it allows a visualized quantum circuit. Starting with an initial qubit state, gates are put at appropriate positions and orders. When the circuit is fully composed, the system automatically runs the circuit repeatedly using concepts of superposition and entanglement. The result is plotted in a histogram format since quantum system is not discrete but probabilistic. IBM Q has also founded an open-source quantum computing software development framework called Qiskit. Along with the visualized quantum circuit, Qiskit uses programming languages like Python to create quantum circuits. The workflow using Qiskit consists of two stages: build and execute. Build, as you can already assume from the word itself, allows you to make quantum circuits that represent the problem you're solving. Execute is a step that allows you to run them on different backends. When finished, the circuit can be simulated on the IBM Q Cloud Simulator, and the accurate histogram will be attained. There are various types of Qiskit. To give some examples, Qiskit Intelligence tackles problems in the artificial intelligence domain, while Qiskit Chemistry deals with the domain of quantum chemistry, including ground state energy, dipole moments, and dissociation plots. Just from the two examples, we can understand that application of quantum computing on numerous areas is possible, and that quantum computing has unlimited potential. When fully developed, IBM Q and Qiskit might allow us to understand nature itself. Quantum computing seems like a very hard topic to explain, but by inspecting parts of it, we can see that it is not only easy to understand but has great potential in the future. Although quantum computing is something that might one day be considered usable for everyone, right now the computers are still being designed for specific tasks only. Other than cryptography mentioned earlier, other current and prospective applications include efficient simulation of quantum systems through quantum computing, which would allow us to study the interactions between atoms and molecules. This could help us design new drugs and materials. Quantum computers are also fast at searching through a space of potential solutions for the best solution in a given situation. Such functions are most applicable in the fields including machine learning, supercatalyst design, battery chemistry, and material science. In January 2019, IBM Q unveiled System 1, a dazzling and delicate machine that's now the first integrated universal quantum computing system for commercial use. Like this, many companies, scientists, and engineers around the world are working hard to create practical uses of quantum computing. The possibilities of quantum computing are only bound by human imagination. And one day, we hope to soon live in a future where we can use quantum computers to make YouTube videos.